Okay, good. Okay, so today's topic, if we look, let's just look at this picture real quick. I've got a curve here, curve below it, and we know now how to calculate that shaded region between some start point and some end point. So essentially that's what's going on here, but now let's talk about what it represents. Okay, so one application here that we call the Gini index, and if you've ever heard of that, it's a measure that different countries can provide a measure of the Gini index, and it establishes a meaningful number with regard to the distribution of income in that particular country. So let's talk about this curve here. Now this is going to be the top curve, and that's just a simple y equals x, f of x equals x. So it's just a slope one line through the origin. And since our x-axis represents the percent of families, and then the y-axis is a corresponding percent of income distributed, if I get to 20% of the families, then in a perfect world, I would have used up 20% of the income. So a perfectly distributed income would fall right on this line. But that's not how the real world works. Usually you've got a mixture of different varying degrees of wealth in your society. So what this curve here below it is the actual, this is like perfect situation, and this is the actual situation. So for the actual situation, what we do is take some data points. So for income level under 20,000, so the 20% of the population, but they're only utilizing 3% way down here of the income or the wealth in that country. And so at 40% of the population, and we're just looking at around 10 or 11% of the income distribution. So if this becomes way down here, we can see that that's a very poor distribution of income, these points down here. But of course, by the time you get to 100% of the population, you're going to use up 100% of the country's income. So you're always going to hit the 1, 1 coordinate, and you're always going to start on the 0, 0 coordinate. And you just get your data points here, and then you do a fit. You try and fit a model function to those data points to give you a good curve for the actual situation. And then the Gini index, you can see down here what that is. Now, if I were to just take this triangle and calculate the area of that entire triangle, well, since this is a 1 by 1 box, the area would be 1/2. So the max area of the triangle underneath this diagonal is 1/2. So we're going to multiply it by 2 so that the range of the Gini index falls in between 0 and 1. Now, if you've got a very equal, or the more fair or equal distribution of income, means your Gini index is going to be smaller, because the actual situation would lie closer to an even distribution of income. And the larger the Gini index, that means the less equally distributed among the families of the income. So you've heard like Bernie Sanders talking about the top 1%. So that's basically if my line looked like this, and then just shoots up there, and you've got this huge area calculation, multiply it by 2, and you're getting pretty close to 1, which would be a terrible distribution of income. So that's what this calculates, and it uses this integral. Now, the reason it's calculated like that is because the top curve is y equals x, so we're going to say x minus, and then this curve is going to be determined by each separate country as they calculate data points and fit a function to their data. Okay, so that's kind of a rundown of here's just some data points for United States in 2011. So we can see that it's certainly significant area. Okay, so let's do examples. All right, I thought I had pasted something in there, but let's look something up here. Okay, so let's say that some country has, and this part here, this is called the Lorenz curve, the one that actually models the distribution of income for a given country. So we're going to say some country has a Lorenz curve, it's f of x equals x to the 2/6. Or better yet, x to the power 2.6. I'm not sure what I said there. Okay, so what we're going to do is find the Gini index for this country. And this is in 2013. And the predicted Lorenz curve for 2025 is g of x equals x to the 1.8. Okay. Let's do this. All right, so our goal is going to be to find the Gini index. Now, obviously, since my Lorenz curve is different in 2013 from what we predict it to be in 2025, we're going to decide if we've improved the distribution or whatever. That's what we'll discuss once we take a look at this. Okay, so our calculation is the integral from 0 to 1 multiplied by 2 of x minus, in this case, in 2013, x to the 2.6 dx, so 2013. Okay, so this is going to be 2 times x squared over 2 minus x to the 3.6 over 3.6, running from 0 to 1. Now it's kind of nice that 0 is the lower limit because that's going to make that calculation easy, and 1 makes this calculation easy. So this is nice and neat in terms of our bounds. So this will be 2 times 1/2 minus 1 over 3.6 minus 2 times 0 minus 0. So this won't even factor in. Okay, so that's going to be equal to 2 times, if we punch that in a calculator, we're going to get something roughly equal to 0.444. It's pretty high. Okay, so that's, remember the area is between 0 and 1. Okay, so that's almost 1/2. So let's see if we're in better shape in 2025. Okay, so they've just been trying to manage some of the components of their economy over the course of this year, and hopefully they've gotten the income to be more equally distributed. Okay, so not a lot's going to change here. We're still going to have x squared over 2, but this will be x to the 2.8 over 2.8. Okay, so that's going to be 2 times 1/2 minus 1 over 2.8. And this is roughly equal to 0.286. Okay, so okay, we can see that this being a smaller area, this means that Lorentz curve is closer to the equality. Okay, so that's Gini index, and that's an application we can use for integration. Let's move on to another concept here called continuous income stream. Just to kind of break in the idea here, let's say that you receive $2,000 a year, and instead of getting this lump sum of $2,000 right after the year, like instead of just getting a check at the end of year 1 and another one at the end of year 2, we're going to think of it as being incrementally distributed to you, even more than incrementally, continuously distributed to you, so that the portion that you got at this time in a quarter of a year is a quarter of the amount you get at the end of the year. So in this case, it'd be a quarter times the $2,000. We've got this constant. So we're back to a rectangular calculation. Just give me this part right here, and I can calculate the area by taking the height times the width. So $2,000 times a quarter of a year, and then $2,000 times half the year. So we're talking 500 and 1,000, and then, but we could break it down to any place between the beginning and the first year just by getting more and more a fraction of any value that we want, or a decimal of any value we want, and we can pick that anywhere out here. So that's what we mean by continuous. Instead of just chunking it 1 year at a time, it's a continuous flow that we're receiving the money. So that's kind of a rundown of continuous income stream. Now, we're not going to generally deal with something so simple as a continuous flow of a constant value per year. So instead, income fluctuates usually in a business. So that means that our model for the rate of change is going to be a little more complicated than this. So in this case, you can't really see it, but this curve actually is bending if, for instance, it represents this function. So this is not going to be a rectangular calculation, so we know we can find the area under the curve using the integration. So in a business, fluctuates over time. You're getting more by the end of this year than by the end of this year. So what we'll do is use the function that matches this as our income, and we're going to, this allows us to find the total income over any period of time. I could say after the first 2 years, what's your total income? So we'll just integrate from 0 to 2. Or if we just wanted to know how much total income was generated between the first and third year, then we could integrate that portion and take into account this very slight curvature. So let's do this. Let's take and find, so this is the rate of change, or the rate of income. And T is time in years since the machine was installed, and the rate of change of income produced by a vending machine is given by this right here. So we're going to find the total income over the first 5 years. So I'm going to go ahead and bring the constant outside. Okay, and then can you see what kind of integration we need to do here? We could use integrate by substitution and let u equal 0.04t, and that's a pretty simple one with this. Now, since we've played around with the calculator a little bit and we're actually using this for an application, let's tap into the calculator. It's that other one I want. Okay, so we're going from 0 to 5. And our function is 5,000 e to the 0.04t. And since I'm using x, I'll make that x. Okay, so there it is. We got about 27,675.34. A lot of writing. I want to make sure that describe what we're answering. Okay, here's a different question. Find the income generated during the second year of operation. Well, this is the first year, and then the second year goes here. So that just implies that we want to know how much we made after year one ended up to year two. Okay, so just a slight change in our calculator. Okay, so total income generated during second year is about $5,309.54. All right, and so that's the curve. You can also put that curve in a y equals. And do it that way. So if I made this my function 5,000 e to the 0.04 and then I can do a zoom. Well, you can start with zoom standard. That's not going to work for this though because of the size of our output being way up there. So if you don't see your graph, you can go in and do a zoom fit. Where's zoom fit? Or you can just create the window yourself. Okay, so that does a little better job of showing you the graph. But we know from our output here that 27. So if I just took f of 0, I'm going to get 5,000, and then I can take and see that after 5 years, I can take f of 5, and then I know what the max is on that. But here, once we got it in our window, we can do the other way. So I can do a second calc and say my lower limit and hit enter. And then go find an upper limit. So say after about 3.5 years, so we'll go with 3.5. It tells me that $18,697.11 in the first 3.5 years or so. Okay, so and then something like this, you know, it's fine if you've got the calculator handy. We're doing an application, so we're not really practicing your integration skills at this point. But you can also do it like we did on this last page in that example, doing it with the algebra. Okay, goal today was to break into just some applications of integration. We actually got through that quicker than I expected, but are there any questions? Okay, because I just want to give you some time to think out a few applications at a time, so I don't really want to break into another one. We will look at 1 or 2 more applications, and then we'll get into integration by parts, which is just one last technique of integration that we'll learn. And then pretty much at that point, I'll have your final review ready for you, and we'll go from there. And I don't think I'm going to give you another test before the final, just because of the circumstances that changed. And I guess we could do a little vote. Would you guys rather have, let's see if I can get one of those things going. All right, I'm going to unshare that. First, I'm going to stop recording.